Hey everybody, and welcome to our next video, which is all about Lewis dot structures, VSEPR theory, and polarity. So we're going to get quite a bit of practice with each of those topics in this video. So hopefully in Chem 1, you started to draw Lewis dot structures. So a Lewis dot structure is a diagram that shows the bonding between atoms in a molecule and the lone pairs of electrons that may exist in that molecule. If you had me, I know many of my students get very comfortable with drawing Lewis dot structures, which I'm always very happy about. They're almost like little puzzles, I guess, with the elements. So based on how many valence electrons those main group elements have, we can show how they're going to combine with other elements. So here's just a whole bunch of examples of Lewis dot structures, just so you familiarize yourself with what they are. So we have water, for example, and its Lewis dot structure, carbon tetrabromide. We have nitrogen. We have, I believe this is phosgene, pH3, hydrazine, and you can even start drawing more complex Lewis dot structures like acetic acid, which is that one down in the corner. Every one of these elements, with the exception of hydrogen, follows the octet rule. They all have 8 valence electrons that are surrounding that particular element, whether they're being shared with another atom or they might be taken away, which normally we don't show electrons being taken away in a Lewis dot structure. That's a whole different story. I'm not going to get into that now. Anyway. And when we draw those Lewis dot structures, we can help to determine the shape of those particular molecules and compounds. So we're going to talk about everything now, and we're going to put it all together at the very end and do some practice problems there. So shapes of these molecules, not only can we draw the actual structure, but the shape of them matters because it helps us to determine why certain molecules react the way that they do. And that's known as VSEPR theory. And VSEPR theory stands for valence, shell, electron, pair, repulsion. And that means that because electrons don't like each other, electrons both have negative charges. So negative and negatives repel. Because they repel, electrons want to be as far apart from one another, and therefore, molecules will adopt specific shapes, and that's to ensure that those electrons are, in fact, as far apart from one another as possible. And that gives us 5 basic shapes. If you decide to take AP chemistry, there are more than 5. We are just going over the 5 most basic shapes that we cover in Chem 1. And again, this is known as VSEPR theory. This is what we call a theory because, of course, we cannot see atoms with our eyes or under a microscope, but we have a lot of data that proves that this is in fact true. So the first shape that we have is a linear shape, and you have all of the information that you need to determine what shape a molecule is in that actual table in your notes. So you just need to write the name. This is an example of a linear molecule. So if I have carbon right here in the center, this carbon, so number of atoms bonded to the central atom, this carbon atom is bonded to 2 atoms, doesn't matter that they're double bonds, and this carbon has no lone pairs. So because of that, this is a linear shape, that is a straight line. Bond angle, 180 degrees, because it is a straight line. So these electrons here and these electrons here want to be as far apart from one another as they can, which means it's a straight line. And there's just a couple of other examples down there at the bottom. I'm just going to breeze through these quick, like I said, because we'll do some sample problems in the next sample problem in the notes. The next shape is trigonal planar. And this is when your central atom, so in this case boron, number of atoms bonded to the central atom is 3. So this boron is bonded to 1, 2, 3 other atoms. And this central atom boron has no lone pairs. That gives a molecule a trigonal planar geometry. Bond angles here, you don't need to memorize bond angles, but they are in fact 120 degrees. So if you think of a circle has a bond angle of 360. 360 divided by 3 equal areas gives me 120. So this is a 120-degree bond angle, as is here, as is here. And there is an additional example right there, which is a CH2O. That is also the formula for formaldehyde. Next shape is tetrahedral. And in this case, your central atom, remember it is always the central atom. This central atom is bonded to 4 other atoms. So it is 1, 2, 3, 4. And your central atom has no lone pairs. When I have a molecule that has this type of arrangement, we say that this is a tetrahedral shape. Now, on paper, this looks like a 90-degree angle. However, we have to remember that in real life, this is not going to be flat on a paper. It's in 3D. So we can actually get these bonds, these electrons, to be farther apart from one another than 90 degrees. And the way you would do that is if I have this bond coming out of the page, and if I have this bond going in to the page. It's kind of hard to visualize, but you can look this up and you might be able to see a better 3D structure of that. But the bond angle here is actually 109.5. Remember, you do not need to memorize bond angles in this course, but it is larger than 90 degrees because these are not flat molecules in real life. Now we are introducing lone pairs on the central atom. So when your central atom, in this case nitrogen, is bonded to 3 other atoms and it has 1 lone pair, we say that this shape is trigonal pyramidal. So it's going to have more of a pyramid shape. It's not going to be totally flat. It's going to be kind of jutted up on one side. But then you have a lone pair of electrons in there as well, which is taking up a lot of space towards the top. And we say that this is trigonal pyramidal. Notice it is not the same as tetrahedral because we do have a lone pair on that central atom in place of a bond. And it is not the same as trigonal planar because trigonal planar does not have a lone pair. So you do have to memorize these 5 different shapes. There's only 5 of them, so it shouldn't be too difficult for you to memorize each of these. And the last one is bent. So water is a bent molecule, and we always want to look at that central atom. So your central atom is oxygen. That oxygen is bonded to 2 other atoms, and it has 2 lone pairs. When I have this particular arrangement, 2 atoms bonded to the central atom, and when I have 2 lone pairs, we say that that shape is bent. Again, this is not going to be a straight line because in 3D, those electrons want to be as far apart from one another as they can possibly be. And 90 degrees, so if I have an oxygen in the middle and a hydrogen on both sides, that means I would have a lone pair on the bottom and a lone pair on the top. They're still 90 degrees apart from one another, but they're going to arrange themselves in a way where they're going to be kind of more than 90 degrees. I guess it's very hard to show this without actual models in front of me, but it takes on a bent shape. If you're having trouble visualizing it, look them up online. You might be able to find really good like animations of what I'm talking about. And those are the 5 different shapes of molecules. And that brings us to polarity. Based on a compound's Lewis dot structure and based on their shape, that particular molecule can have other properties that are dependent on their polarity. And the polarity is whether or not we have a positive side of a molecule and a negative side of a molecule. This is going to be very important in this class in one of the later units we talk about, all about intermolecular forces and types of solids. So polarity is the unequal attraction of electrons in elements of a compound that results in a molecule with a positive end and a negative end. So water, for example, what we just talked about, that bent molecule, because it is bent, it is not symmetrical on all 4 sides. So this bottom side of the molecule has a much more negative charge than this top side of the molecule. And that's because oxygen is much more electronegative than hydrogen is. You might remember talking about electronegativity in Chem 1, fluorine being the most electronegative, oxygen and nitrogen being not too far behind in their electronegativity. This basically comes down to symmetry. So when determining the polarity of a molecule, it's all about symmetry. So if I look at this molecule up here on the left, this molecule is nonpolar. And if I look, this carbon is bonded to 4 other chlorines in all 4 directions in this tetrahedral shape right here. This actually shows you a really nice 109.5 degree bond angle right here. But anyway, it's symmetrical on all 4 sides. This carbon is being pulled on equally in all 4 directions. It's a totally symmetrical molecule, which means that it's nonpolar. This molecule, on the other hand, I have a carbon in the center bonded to 3 other chlorines, but one of those is a hydrogen. This is not a totally symmetrical molecule. It might be symmetrical going across this way, but if I draw a horizontal line, it's not symmetrical that way. This side of the molecule would have a much more negative charge because chlorine is much more electronegative than hydrogen is. This is a polar molecule because it is not symmetrical. This one is because it is symmetrical. This one is a polar molecule because it is not symmetrical. And this one is a non-polar molecule because it is symmetrical. So it's kind of backwards in that sense. The polarity of a molecule depends on the electronegativity of the elements that make up the molecule and how they're arranged. We'll go into electronegativity a little bit. And if a molecule's central atom has a lone pair, my rule of thumb, it will always be polar. If you have a lone pair on a central atom, it is not going to be a symmetrical molecule across all planes, so therefore it will always be considered polar. So here we go. Asymmetric molecules tend to be polar. So let's go ahead and look at hydrofluoric acid right here. So this is not symmetrical. Of course, these are 2 totally different elements. And fluorine is much more electronegative than hydrogen is. Because of that, this side of the fluorine molecule, more electrons are going to live on that side right there. So if I were to try to draw this out as best as I can, more electrons exist over on the fluorine side right here. And you might just have a couple electrons on the opposite side. Because fluorine is more electronegative and it wants electrons more of your electrons live on this side because fluorine can pull them towards itself. And when that happens, since electrons have a negative charge, this side of the molecule will have a partial negative charge. The way we draw this is a Greek letter delta, and we draw it, it's like an S with like a little thing that comes off of it, or you could draw an unfinished 8 like that. That's a delta. And it's partially negative, and that's because more electrons live on this side of the molecule because it is more electronegative. This side of the molecule would be partially positive because electrons are not really present on that side of the molecule. Same thing goes for water. So like we said, anytime you have a lone pair of electrons on that central atom, it has to be polar. But because across this bond, because oxygen is more electronegative than hydrogen, across this bond, we're pulling electrons more towards oxygen. So more electrons are going to live on oxygen across this bond. I'm still going to draw 1 or 2 over here. And across this second bond, again, there's electrons being shared, but more electrons are going to exist on the oxygen. Because you have a much higher electron density across both of those bonds, which leads to the oxygen, this is going to be a polar molecule. And wherever you have more electrons, this side of the molecule has that partial negative charge. So there are more electrons on this side, meaning that that side of the molecule has a partial negative charge. These guys will have a partial positive charge. Again, it all comes down to the more electronegative molecule, or the more electronegative atom within the molecule. Remember that your most electronegative, I'm going to abbreviate electronegative here, is fluorine. Anything close to fluorine is going to be very electronegative. So elements like oxygen, nitrogen, chlorine, bromine, maybe even sulfur, right? Typically the ones that you're going to see that have very high electronegativities. Let's look at symmetric molecules. So in this case, symmetric molecules are always nonpolar. So a good example of that is methane, which is carbon tetrahydride. I have carbon in the center, and I have 4 hydrogens on all sides of this. And in this direction, this bond right here, carbon is pulling electrons more towards itself, right? Because carbon is more electronegative than hydrogen. Same thing here, pulling electrons towards itself, pulling electrons towards itself, pulling electrons towards itself. Even though every one of those bonds is polar, because this molecule is totally symmetrical, there is an equal pull in all directions, which makes this a non-polar molecule. So because carbon has an equal pull on all 4 hydrogen atoms, this is non-polar. So no partial charge is needed because this does not have a partial positive side and a partial negative side because it's totally symmetrical. Same thing here. So here's my plane of symmetry going down right there. This bond, sulfur, is a little more electronegative than carbon. So electrons get pulled in this direction, but electrons also get pulled in this direction. But because they get pulled the same amount on both sides, it's a nonpolar molecule. Totally evens each other out. So it has to do with symmetry. It's what it comes down to. If you need more help with this, by all means, let me know in person. I'll be more than happy to go over this with you in class, but it does always come down to symmetry. At this point, let's go ahead and do the sample problem in the notes and get some practice with drawing Lewis dot structures and determining the shapes of those Lewis dot structures, and then determining if those molecules are polar or not. So let's dive into the notes. All right, so before we do a sample problem 7 in the notes, I just want to show you how to determine the number of valence electrons that a particular element has. We kind of talked about this a little bit with electron configuration, but I just want to show you quickly where I'm getting these numbers from. Everything in this first group, so hydrogen and your alkali metals, these all have 1 valence electron. Everything in your alkaline earth metals group, these guys all have 2 valence electrons. We skip the D block here because they can vary in the number of valence electrons that they have, and your lanthanides and actinides down here towards the bottom. Boron's group, these guys all have 3 valence electrons. Carbon's group has 4, 5, oxygens has 6, halogens have 7, and your noble gases have 8, with the exception of helium, has only 2 valence electrons. When I start drawing the Lewis dot structures in sample problem 7, this is where I'm getting each of those numbers of valence electrons from. Just so you know, if you're confused, like, wait a minute, why is nitrogen 5? It's based on where it's located in the periodic table, based on its electron configuration. So using that, let's go ahead and do this guy right here. Let's go ahead and just do the Lewis dot structures first for each of these. Then we'll go through and determine shapes, and then we'll go ahead and determine polarity. I think it's just easier to do it that way. So in this case, we're going to draw the Lewis dot structure for diatomic chlorine. So chlorine has 7 valence electrons. So you want to show those 7 valence electrons using dots around all 4 sides. I like to imagine a little box around it. And we're just going to pick a side. It doesn't matter which one. I'm just going to pick the top here. So there's 1, 2, 3, 4, and I'm going to go around again. 5, 6, 7. You always want to unpair those electrons before you go ahead and double them up and pair again. Now this particular molecule has just 2 chlorine atoms. So I'm going to draw another chlorine with 7 valence electrons around it as well. And I'm drawing it this particular way just to show how the bond is going to be between each of these. And I think that as you progress with drawing Lewis dot structures, you'll start to get more comfortable with drawing the lone electrons, these ones that are unpaired in the right place. You always want to connect the electrons that are not paired. So this chlorine has 7 valence electrons around it, and so does this chlorine. It has 7 valence electrons around it. These guys here, these electrons don't want to bond. These are already in a pair, so they're happy. Same thing here. That's already a lone pair. They're happy. These are a lone pair, and same thing goes around this side here. The only electrons that want to bond are ones that are unpaired. So in this case, we can go ahead and draw a covalent bond or a line in between both of those chlorine atoms. And in this case, this is showing that this electron from the chlorine on the left is being shared with this one on the right. So this chlorine now has 8 electrons around it. And then this chlorine on the right also has 8 electrons surrounding it because it's sharing the 8th one over here. This is the correct Lewis dot structure for diatomic chlorine. Now, of course, we don't want to show those lone pairs with X's on them. So I'm just going to redraw this here. And here is the correct Lewis dot structure. So you're showing how those unpaired electrons are being shared between each of those chlorines. Let's go ahead and try oxygen here. So oxygen has 6 valence electrons. So here's 1, 2, 3, 4. I'm going to go around once, and then I'll go around again. So I have 2 lone pairs on oxygen. Now you'll see oxygen has 2 unpaired electrons, which means it wants to bond 2 times, which is convenient because it's bonded to another oxygen that also wants to bond 2 times. So I'm just going to draw a mirror image of those, and I'm just going to show that this lone electron wants to be in a bond. It wants to share with another one. So we're going to essentially connect the dots between both of those oxygen atoms, but we're not done because I still have an unpaired electron on the bottom here and an unpaired electron on the bottom here. So it actually wants to bond again. I have a double covalent bond. And please make sure you connect the dots when you do this, because a lot of times students won't connect the dots and it drives me nuts. That's a really ugly Lewis dot structure. So what we're going to do is we're just going to draw that oxygen with a double bond in between it and another oxygen with 2 lone pairs bonded to it. That's basically what it comes down to, is you just kind of have to take your time with these and figure out how these atoms are going to bond to other atoms and how many times they're going to bond to them. Let's try the rest of these in this row here together. So hydrogen and oxygen. You never want to put hydrogens in the middle because hydrogen only wants to bond 1 time. So we're going to put oxygen here first. 6 valence electrons. And notice it wants to bond 2 times, which is convenient because it's got 2 hydrogens that it wants to bond to. And each hydrogen has only 1 valence electron. So I can go ahead and draw a bond there and there. But there are 2 hydrogens that attach to this water molecule. So there is the second one right there. D, let's go ahead and draw this one. So silicon has 4 valence electrons, so it wants to share 4, and fluorine only wants to share 1 each. So we're actually going to draw silicon in the middle. You might remember me saying in Chem 1, least electronegative other than hydrogen goes in the middle. So silicon has 4, that's going to go in the middle. And fluorine has 7 valence electrons. So let's draw fluorine on this side. 1, 2, 3, 4, 5, 6, and 7. Notice fluorine wants to bond once right here. So I'm going to draw 1 bond in between that fluorine and that silicon. Silicon's not done though, because there are 4 fluorines that want to bond to this. So you actually have to connect fluorine 3 more times with 3 different fluorines. The formula is SiF4. So you want 4 fluorines that surround this, like so. And those lone pairs are important. So you do need to include lone pairs. I know they're a pain in the neck to draw. Trust me, I've been doing chemistry most of my life. I get it. But they are important to the overall structure and the reactivity of that molecule. I want you to try the rest of these on your own. I feel like if you could do these first couple, it kind of brings back memories. I've been teaching Chem 2 for a long time, and students just kind of fly through this, and they're like, oh yeah, I know how to do this. This is good. So pause this video now and try to do the rest of those in this sample problem, and I'm going to have the answers for you once you unpause the video and you come back so you can check yourself. All right, so here are the answers for E and F. Sorry, my handwriting is so sloppy. I have this like little pad that I write with, so it writes on the computer screen, and it's not always the easiest to write with. So my handwriting in real life is much nicer. There's E and F, and you can pause this and check G through J, and then there is K and L right there. From there, let's go ahead and determine shapes. So now that we have these Lewis dot structures down, let's determine the shape. I'm going to do shapes in pink right here. This particular molecule only has 2 atoms. So because these are 2 atoms, it has to be linear. It has to be a straight line, right? It can't be any other shape. Same thing with B. This is diatomic oxygen. This bond right here has to be linear. So the shape of this molecule is linear. These first 2 are easy. Any molecule that has only 2 atoms has to have a linear shape. For C, we always want to look at the central atom. So your central atom here is oxygen. It's the one that's in the middle of everything that's going on. And this central atom is bonded to 1, 2 other atoms and has 2 lone pairs. So I'm just going to number the atoms, and I'm going to circle the lone pairs. And if you look at the chart in your notes, the shape of a molecule that would have those characteristics is bent. So any molecule that is bonded to 2 other atoms and has 2 lone pairs on the central atom is bent. Silicon tetrafluoride, this silicon right here is right in the middle. So we have to look at that one to determine the shape. This silicon atom is bonded to 4 other atoms. In this case, they are 4 fluorines. And silicon has no lone pairs. Even though there's lone pairs on fluorine, it doesn't matter. You're only looking at the atom in the middle. So the shape of this molecule must be tetrahedral. Tetrahedral. E, again, we're always looking at that central atom right here. So that central atom is nitrogen. This nitrogen is bonded to 1, 2, 3 other atoms. And that nitrogen has 1 lone pair. And if you look at your chart, the shape of this molecule would have to be trigonal. And this is a pyramidal. Because it has that lone pair. And actually, F is the same exact thing. This is still a nitrogen that has 1 lone pair, and that's bonded to 3 other atoms. It doesn't matter. that we're replacing a hydrogen with a chlorine, it still takes on that same shape. So this is still trigonal pyramidal. Let's look at G. Central atom is carbon right here in the center. It's the only one we care about. This carbon is bonded to 1, 2, 3 other atoms. It does not matter that one of these is a double bond. All you're doing is you're counting the number of atoms it's bonded to. And there are no lone pairs on carbon. So in this case, it still has that trigonal because it's still bonded to 3 other atoms. That does not look like a G. But this is trigonal planar. So notice the difference between G versus the ones prior to this. So G does not have a lone pair on the central atom, but E and F does. So just be careful of that little difference between the two. You go ahead and do H and I. Don't worry about J, K, and L. They have multiple atoms that make it up, so there's not really one shape for the whole molecule. But just try H and I quick. Pause this video. Here we go. Determine the shape. And there we have it. So H is trigonal pyramidal, and I is bent. Let's try polarity quick. So A, let's do polarity in green. So this chlorine, there's only one bond, and because this is only one bond, each chlorine has an equal pull on each other. Because this is totally symmetrical, neither one of those chlorines wants electrons more than the other. This is a non-polar molecule. And actually, the same thing goes for O2. Here, none of these atoms wants electrons more than the other. So in this case, they cancel one another out. It's totally symmetrical, non-polar molecule. Let's look at C, water. Now, water is not symmetrical. So one of the rules of thumb that I have is that when you have a central atom that has a lone pair, it has to be polar. We have to have a polar molecule here. And that's because across this bond, oxygen is more electronegative. It's pulling electrons towards itself. And across this bond, oxygen is pulling electrons towards itself, which means most of your electrons are going to live on this oxygen, meaning this side of the molecule has that partial negative charge. And this side of the molecule has your partial positives. That's what makes it polar, the fact that it's asymmetrical like that. For D, notice here that this silicon is bonded in 4 ways to fluorine. This is a totally symmetrical molecule. It's symmetrical this way, and it's symmetrical this way. So this is going to be a very nonpolar molecule. No partial charges whatsoever. There's no side of the molecule that's more negative than the other. Again, my rule of thumb, if there's a lone pair on the central atom, has to be polar. So, which side of the molecule is going to have the partial negative or partial positive charge? Let's look across the bonds. So here, nitrogen is much more electronegative than hydrogen. So we're going to have a pull going towards nitrogen. Same thing here. Nitrogen's more electronegative, so more electrons are getting pulled towards nitrogen. And actually the same thing here. So this lone pair at the top, this nitrogen is going to have that partial negative charge. And all of these hydrogens will be partially positive. Partially positive. And actually the same thing goes for here. So nitrogen is still going to be partially negative because nitrogen is far more electronegative than everything else. This guy's also going to be very, very polar. Maybe not very polar, but it is polar. Let's try the next, try the rest of these here. This guy, very polar, not symmetrical. It might be symmetrical this way, but you're not going to be symmetrical going across. So this is a polar molecule. Who's the most electronegative? Oxygen. Oxygen's much closer to fluorine. So this side of the molecule has the partial negative charge. This side of the molecule has your partial positive. H, check it out. H has a lone pair on the central atom. Because it's got a lone pair on the central atom, it's got to be polar. Actually, the same goes for I. I also has to be polar. It's got lone pairs on that central atom. In this case, your fluorine is actually more electronegative. So across this bond, poles going towards fluorine. And across this bond, poles going towards fluorine. So fluorine here has your partial negative charges. And your oxygen is partially positive. So it all depends on what they bond to. This one I'd have to look up electronegativity values. I'm not 100% sure who's more electronegative. I would guess phosphorus, but I'm not 100% on that. So I'm just going to leave partials out of that one. This guy's going to be polar. You got some lone pairs there. Guess what? This guy's also polar. You have some lone pairs there. This guy, totally symmetrical. Symmetrical that way, symmetrical that way. Non-polar molecule. I think drawing Lewis dot structures is pretty self-explanatory, and I think that determining shapes is also pretty self-explanatory. But if you have trouble with polarity, please email me or let me know. Come and see me when school starts. I'll be more than happy to review this with you. There is a page in your notes that, or a worksheet in your notes that kind of goes through this. So try these out for yourself. And remember, it all comes down to symmetry. So remember that if you have a symmetrical molecule, that molecule is nonpolar. And if you do not have any lone pairs on your central atom, you might have a nonpolar molecule. Anytime you do have a lone pair, it is always polar. So don't hesitate to reach out if you have any questions, and we'll get ready for the next video, which is all about chemical binding. So it ties into this really nicely. Anyway, I will see you then, and have a wonderful day. Bye.